give this talk. When they first asked me, would you like to do this? My answer was, of course, sure, sounds like it would be fun. And it was only a moment later that I got to thinking that I should maybe ask what the talk is about. And so I asked, and said, well, we're just looking for an overview of physics. And I'm thinking, physics? How long is this talk? 45 minutes an hour? Does that sound good to you? I didn't know what I was going to do the other 35 minutes. But, so normally, when I'm in front of an audience like this, when I'm in front of the audience, the natural inclination is to start explaining some lessons of physics. And that's clearly inappropriate for the time slot here. I'm accustomed to explaining physics over the course of an entire semester and then running out of time. So I can't do that really today. It's both inappropriate for the time slot and probably also for the venue. So what I'm really going to do today is not really trying to explain physics. I'm going to limit myself to just plain describing it and kind of trying to describe the scope of physics and kind of what the types of things are that physicists think about. And so that's going to be kind of the layout of my talk. This overview and kind of identifying categories of physics, that's actually most of the talk, trying to figure out kind of what is the scope of physics and how far does it reach and what kinds of things are included in there. But there's an ulterior kind of underlying motive in all of this. As we discuss kind of the content of physics, I'm really trying to get you to focus on how physicists think, especially as they view their own discipline. And the idea there is maybe that's the most appropriate thing for this audience, because you guys actually are forced to interact with physicists every once in a while. And physicists share a lot of common idiosyncrasies and peculiarities with other academics, but there's some peculiarities and idiosyncrasies that are all their own. And it might be useful to be aware of them. Preserve your sanity and actually talk. So that's kind of the theme of the talk.
Sir,
today.
could you speak up just a little bit?
I'll do my best.
Okay, thanks.
That's kind of the theme of the talk today. As we kind of go through this content of physics, you'll discover that there's a couple of characteristics of all of the discussion. Physicists are mostly focused on the simplest, most basic underlying explanation of whatever physical phenomena they're looking at. And that's kind of a recurring theme that you'll see kind of throughout all the different aspects of physics that we're discussing today. At the very end of the talk, if we have time left over, and I think it's a 50-50 chance whether we get there, I'll actually try and make some specific comments about the kind of resources that physicists use in their research and in their teaching that you probably know about, but you should definitely keep in the forefront of your mind when you're trying to help physicists. So I should start, I suppose, by telling you a dirty little secret about physicists. Or maybe it's not a secret, maybe you'll all know this, you can tell me. Physicists are kind of arrogant. You know that? They're kind of arrogant. They believe that physics is the source of all scientific information. And they believe this, in my humble opinion, they believe this because it's true. Okay, that really was intended as a joke. But if I explain to you where that comes from, it actually teaches you something about how physicists think about their work and the things that they do. So if you study physics at its most basic, at its most fundamental, say you study particle physics, I'm trained as a particle experimentalist, this is the way I do a lot of the time. If you study particle physics, you're engaged in trying to figure out how all of the pieces of the universe fit together and interact in order to build the experience we have in everyday life. So you study how quarks bind together to form neutrons and protons, and how neutrons and protons bind together to form atomic nuclei, and how they can capture electrons to form atoms, and how atoms stick together to form molecules. And in principle, once you've got all of that, you have derived chemistry. Right, because that's what chemistry is about. It's how atoms attach to each other and how molecules attach to each other. So in principle, you can derive from those basic laws the entire foundation of chemistry. Now, you wouldn't really derive all of chemistry that way because it's not practical to do so, and terribly confusing, and there are a lot of ways in which you'd like to approach chemistry, which is not, from the ground up like that, which is presumably why we still have chemists. I think that's why we still have. But in principle, you can derive chemistry from physics in that kind of sense. And then, of course, once you have chemistry and physics, then you can actually derive a lot of other stuff. I mean, if you really do understand all of physics and chemistry, well, then you can pretty well handle all of astronomy and astrophysics, because that's really just chemistry as it is together, and then the laws of gravity as they apply to those big things. And you can pretty well just, pretty well derive all of, I suppose, geophysics. And if you really got chemistry, that includes organic chemistry, so then you ought to pretty well be able to create life from that. So you got all of biology now. If you got biology, that includes the biology of human beings and human brains. So there you got psychology. And then, of course, it kind of naturally leads to all the other intellectual endeavors of humans, including philosophy and economics and religion and politics. There's not much science in politics these days. So in principle, I mean, if you study physics at its most basic, it just follows. And that's the way physicists think sometimes, yeah?
How do you feel about mathematicians?
Mathematics is a very useful tool for doing physics. Sorry, what was your point? Okay, I mean, all of that is said, obviously. But the point I want to make is there's the tiniest grain of truth to that. And there's a little something that really is truthful about that. Physics is really the foundation of a lot of scientific understanding at its most basic level. And that's in part of how physicists think about their discipline. So physicists are very arrogant, that's true. Physics involves the search for the most fundamental explanations of the physical world. That's really the way they think. And that's the way that's the party line by which they advertise their discipline. Now, I gotta really admit to you, that's not actually the reason that physicists do what they do. The reason that physicists do what they do is because their attention span is limited and their memories are very faulty. So really, what they're interested in is read. Physicists are interested in the most simple-minded descriptions with the fewest rules to remember. Because, like, biology with all those Latin names, no way are we going to get all that stuff. No, just give us a few rules and make them simple enough so that we can rederive them, and then we're okay. And that's what we're really after. So I don't have time to actually explain all of physics, but I thought, just for your future reference, in one slide I would actually document all of physics in one slide. And this is everything. This slide actually appears in kind of two parts. On the left hand of the slide are things that I characterize as general frameworks of mechanics. The word mechanics in physics is not the same as the word mechanics in the English language. When a physicist uses the word mechanics, they don't mean what the car repair guy does in the garage. They mean, in fact, a theory of motion, a general theory of motion. So the first kind of modern successful theory of mechanics was invented by Isaac Newton. And it includes his three laws of motion. The most famous is F equals ma. And it's a general theory of motion. It says, it applies to any object. It says if you apply a force F to an object, the result is an acceleration A. And it describes the relationship between the force and the acceleration is related according to the mass of the object. And that's true no matter what object you're talking about. And it's true no matter what force you're talking about. You could be talking about any of a number of different types of forces. You could be talking about gravitational forces, electromagnetic forces, contact forces, any kind of force, it always applies. So we call this, I like to call this a general framework, even though the word theory sometimes apply to that. So this is a general framework for motion, to which any specific theory of any particular type of interaction might apply, like a theory of gravitation or a theory of electromagnetism or a a general framework. And Newton created this general framework for mechanics in the 17th century, and it was incredibly successful. And it reigned supreme for 250 years, more. And then at the beginning of the 20th century, physicists discovered that Newton's framework of mechanics broke down in two regimes that were kind of being explored at that time. First of all, Newton's mechanics was proven to be inaccurate when trying to describe objects moving very fast. And I'm not talking about fast like jet speed fast. I'm talking about fast, really fast, like an appreciable fraction of the speed of light. If you're trying to describe the motion of objects moving very, very fast, Newton's mechanics is shown to be no longer accurate. And eventually that had to be replaced by a theory developed by that young German Albert Einstein, a theory that correctly described not only everything we see in the everyday life, but also things moving very, very, very fast. That theory was called special relativity. It was the new alternative to Newton's mechanics that descended from it. More or less at the same time, there was another forefront of physics which also proved Newton's mechanics wrong in a different way. And that involved the world of the very small. In the microscopic realm, it was clear that Newton's mechanics was no longer applicable, that it broke it down. It did not correctly describe things that were really, really tiny, that were really microscopic. And indeed, the microscopic world was proving to be really quite counterintuitive in general. All of this was going on at the beginning of the 20th century for a couple of decades. In the microscopic world, it was apparent that many of the even basic ideas of just what an object is were breaking down. Objects in the microscopic world don't have well-defined edges. They don't necessarily even have well-defined locations. The characteristics of objects in the microscopic world, it's kind of a different set of characteristics than what we usually think of as applied to kind of everyday objects. There's the particle characteristics, location, speed, size, you talk about of everyday objects, but in the quantum world, they also seem to pick up these other characteristics that we normally apply to things like waves. So wavelength, frequency, and they exhibited wave-like behavior that was not characteristic of what we thought of for everyday objects. They diffracted through openings. They interfered with themselves. They produced interference patterns. So it's clear that a totally new framework was needed in order to describe correctly the microscopic world. And that led, over the course of a couple of decades, to the development of this framework called quantum mechanics. Now that obviously already is just way too complicated for physicists. Because now we got these like two theories, one for fast things and one for really tiny things. And we gotta like carry both of these things around all the time in order to get anything done. And what do you do if you have something that's small and fast? So finally, over the course of several decades, started coming out probably in the 1930s or so, these two kind of frameworks were melded together successfully and consistently into a class of frameworks we call quantum field theories, which described the quantum mechanical world of the very small and also the relativistic world of the very fast, and did so correctly. And this is now the kind of the general framework by which all other specific theories are measured. All other theories of any kind of interaction has to fit within the context of a quantum field theory. Now, of course, physicists don't stop there. They continue to tinker forevermore. And in recent decades, many theorists have been figuring out how to change quantum field theories into something even more interesting, maybe more simple. And there's a whole class of theories now called string theories, which might conceivably become the vogue of the future. And the idea behind them is that what we currently consider a fundamental microscopic particle is maybe not really a particle if you look close enough. If we get to the smallest possible scales, maybe they're actually little loops of string. And each type of particle that we think is a fundamental particle now is actually a loop of string vibrating at a different frequency. And there are all sorts of elegant theoretical prejudices why a theory like this might be a good thing to pursue. The only drawback is no one has successfully created a string theory that describes the world we live in, which is not an impediment for most theorists. And they continue to work on this, but they're not there yet. I mean, they describe worlds that look somewhat like the world we live in, but not entirely. So that's still an open source of inquiry. That's kind of the left half of this slide. And the other side of the slide is all about specific theories that have to fit within, these days, a quantum field theory framework. We currently, and for a long time, have recognized only 4 types of fundamental forces, or maybe only 3, depending on how you count them. There are electromagnetic forces, there are 2 types of nuclear forces and gravitational forces, and all other forces can be described in terms of those forces. The story of electromagnetism is probably the prototypical classic example of how physicists strive to simplify their description of the physical world. It's a terrific example of how physics tries to work. At the turn of the 19th century, scientists are looking into these newfound phenomena involving electricity and magnetism. They're studying static electricity. They're starting to make conducting wires and Leyden jars that store charge and crude batteries. And simultaneously, they're starting to play around with naturally magnetized lodestone and understand, magnetic compasses and things that have been around for a while, and other things in the Earth's magnetic field. And these two kind of paths of inquiry are going side by side in the early 1800s. And people are noticing that there's a lot of similarities between the studies of electricity and the studies of magnetism. Electricity comes in 2 types of charges, positive and negative charge. Magnetism comes in 2 types of poles, south and north poles. The forces have the same distance dependence in some sense. And there are lots of similarities between the two, but they're proceeding kind of side by side. And then, kind of mid-century, a couple of discoveries are made that recognize the connection between electricity and magnetism is even more intimate than we imagined. If you take electric charges and you run them through a wire, if you run electric current through a wire, you produce a magnetic field. So electricity and magnetism is really intimately connected. Like one produces the other. This is the principle behind the electromagnet. And the reverse is also true. If you take a bar magnet and you wave it in the vicinity of a conducting wire, you can produce an electric current in the wire. And that's kind of telling you these two things that we've thought of as separate really go together. And it was in 1873 that this clever Scotsman by the name of James Clerk Maxwell put those ideas together in one consistent theory. And in that year, he published the theory of electromagnetism, which was a fantastic synthesis of everything that everybody knew about electricity and magnetism up to that point. And he put it all together in one concise theory that really demonstrated, kind of from the mathematical structure of the theory, demonstrated that electricity and magnetism, they're not separate things. They're really like 2 sides of the same coin. And his entire theory was for, not only did he summarize everything that happened in electricity and magnetism for the last 80 years, he also recognized, with the publication of this theory, he also recognized that this theory also describes light. Light is an electromagnetic wave. And so in one theory, instead of 4 equations, he described everything with electricity, everything with magnetism, and light. It was like the greatest synthesis ever conceived in the history of physics. And how could it be better? And once you got a theory that fits on a t-shirt, everybody loves it. So that's a classic example of what physicists try to do. I mean, they like to use optical laser in the extreme. They like to try and find the smallest set of assumptions that describe the biggest possible scope. They like to find kind of the most fundamental underlying from which everything else might be derived. Well, that was in the 1870s. And then, of course, at some point, everybody realized they had to somehow incorporate the ideas of quantum mechanics in the microscopic world. So that evolved into a quantum field theory for electromagnetism called quantum electrodynamics. That was constructed in the 1930s in part by this gentleman, Richard Feynman. And then also, along with the same time, physicists were discovering nuclear interactions, of which there are two types. Weak nuclear interactions govern the decay of certain radioactive decay of certain atoms. Strong nuclear interactions describe how neutrons and protons come together in atomic nuclei. This kind of synthesis and unification happened one more time between electrodynamics and weak nuclear forces. So the theory of weak nuclear forces was being developed in the mid-20th century. And then towards the end of the 20th century, a small group of theorists were able to put together the ideas of quantum electrodynamics with all of the knowledge of weak nuclear interactions and construct one theory that described all of that, recognizing nuclear interactions in this case as being kind of the other side of the coin from electromagnetic interactions, and put it together in one kind of nice synthesized, unified electroweak theory. Since then, we've also developed a quantum field theory for strong nuclear interactions, and it parallels the mathematical structure of the electroweak theory. It looks very similar. And nobody has yet succeeded in kind of writing one theory for the two of them. It makes everything look like it really belongs together, although that's a very strong suspicion. And there are indications that maybe if we could only get high enough energies, we could kind of recognize this connection more clearly. And so there's the forefront of physics is trying to understand how electroweak theory eventually is going to unify with our understanding of strong interactions into one big, grand, unified theory. And that's a forefront of physics research these days also. The one outlier in this story is the story of gravitation. It's an outlier because we've never actually succeeded in consistently developing a quantum field theory for gravity, although many people have tried for quite a while now. The first, modern theory of gravity started probably with Galileo dropping balls of Pisa, recognizing certain constants that everything falls at the same rate, no matter what size it is, it still hits the bottom at the same time. That was refined somewhat by Isaac Newton when he came along into what he called a universal theory of gravitation. The universal theory of gravitation took Galileo's ideas of gravity and recognized that gravity applied not only to falling apples, but also the same theory applied to planets orbiting the sun or moons orbiting a planet. That the same gravity that governs how things fall at the surface of the Earth is also the gravity that describes how planets move in orbits. That's the universal theory of gravitation. That, too, was a great simplification. Well, the laws were not any different, but the scope was bigger. So using the same small set of assumptions to describe this stuff. That evolved in the early 20th century into a totally different approach to describing gravity, introduced by this gentleman, Albert Einstein. He had this brainchild that was just revolutionary in so many different ways. It took a totally different tack on how to describe gravity. It didn't describe it so much in terms of forces, but actually described the action of gravity in terms of space-time. So in Einstein's theory of general relativity, which is his theory of gravity, mass and energy warps and distorts space-time. And in response, if you bring up some other mass into that region of warped and distorted space-time, it moves in certain ways according to what the distorted space-time is telling it. And that's the way in which two massive things talk to each other. you don't just do that randomly. There was a reason for doing that. I mean, he developed this theory and recognized that, well, this theory disagrees in small ways from Newtonian gravity, in ways that are very small in most of our everyday life, but might be important in other regimes. And even in our everyday life, you know, if you made sensitive enough measurements, you might be able to notice the difference between Newtonian gravity and general relativity. And indeed, over the course of decades following its publication of general relativity in 1915, it was confirmed over and over again that general relativity is correct and Newtonian gravity is wrong. General relativity also solved one big outstanding problem that bothered everybody at that time. Here's the problem. Newton's theory of gravity says that the force between two massive objects depends on how far apart they are and depends on what the two masses are. And that's the force. And presumably, if you take away one of the objects, then immediately the other object no longer feels that force and knows that something has changed. So for instance, you know, we're talking about, say, the Earth and the Moon. The Earth and the Moon are tugging on each other. The Moon is tugging on the oceans of the Earth, and that's why the tides are held up all the time. And so in principle, if we just like obliterated the Moon, which is an experiment I've always wanted to do, we just immediately vaporize the Moon, then instantly the tides would start to fall. We would know it. And that bugged everybody. Because what is this? Newton called this action at a distance. The modern term for this is non-locality. No matter what you call it, it bugs everybody. It's like voodoo. Right? You stick a pin in something over here and something else happens over there. It's voodoo. Action at a distance is weird. People don't like this. It bugged Newton. Newton basically said, I have to paraphrase it because I can't remember the quote, basically says, nobody who has any intellectual facility at all could possibly believe this is ridiculous. He was talking about his own theory at the time. So this really bugged people. And Einstein solved that with his theory of general relativity. In his theory of general relativity, the gravitational information proceeds through distortion of spacetime. And distortion of spacetime occurs as a result of mass or energy in some location. So the information of the gravitational force propagates as ripples in spacetime. It propagates as gravitational waves in spacetime. And that's how the two massive objects communicate with each other via the gravitational force. And that solves the action at a distance problem because gravity waves only travel at the speed of light and no faster. So nowadays, if we obliterate the Moon, it's 1.3 seconds before we actually notice anything different because the Moon is 1.3 light seconds away. And that's what the theory of general relativity is what we call a classical theory. It does not incorporate quantum mechanics, so it does not correctly handle the microscopic world. And theorists have struggled for decades now trying to generate a consistent quantum theory of gravity. For purely technical reasons, there are some impediments to actually getting that done correctly. But hopefully someday that will happen also, and then maybe we can put all of the pieces together and end up with something that physicists really can handle, that is one theory and one set of rules and one t-shirt that handles absolutely everything in the universe. And we will be calling that the theory of everything. Yes, you all wonder. Okay, so that is pretty much all of physics, and by induction, all of everything else up through politics. So I could quite reasonably end my talk right here, but I just have a few more words to say. About 10 slides worth. And I kind of wanted to actually say, of course this is not the way physicists think on a daily basis. They think about their discipline as how it fits in with the general discipline of physics and categorize themselves in certain ways. And I want to kind of teach you that categorization, even though underlying all of this is what I showed you on the previous page. So if you ask a physicist, what kind of physicist are you? They may answer with a specific subfield, but often subfields are categorized into a few large classes, depending on kind of the size of the stuff that you're studying. So small-scale physics applies to nuclear physics and subatomic particle physics, sometimes called energy physics. Medium-scale physics encompasses an enormous range of stuff, but basically anything that fits in a room or maybe on a tabletop. It includes things like solid-state devices, fluid mechanics, and material science, and most of biophysics, and most of geophysics, and an endless list beyond that. And large-scale physics is kind of things, bigger than planets, astrophysics, and cosmology. Physicists also, in parallel, classify themselves into two camps, either experimentalist or theorist. The way to tell the difference is fairly simple. It might be less easy to recognize. So experimentalists are people who do something useful, potentially at least. And theorists are people who don't know which end of the soldering iron to pull. And sometimes you can't tell the difference from a distance. But so here's a clue for you. So here's a couple of representative experimentalists. This is Georg Binnig, and this is Heinrich Rohr, two Swiss physicists who, in the early 1980s, invented the scanning tunneling microscope, which was a new style of microscope that was capable of resolving images at the atomic scale. This is the first time you could actually see atoms with a microscope. At the time, it was probably the most sophisticated device on the planet. I once heard a talk by Heinrich Rohr shortly after he got the Nobel Prize for this work. And I was tickled pink that someone see this little guy with his Swiss German accent, and he was speaking in front of a crowd of, 5,000 people, and they're kind of setting him up with a projector and everything, and this is 1986 or so. And somebody hands him a laser pointer. He goes, gosh, I don't hand me that complicated technology. I don't believe that stuff. Just invented the scanning thing. In contrast, this is a typical theorist. And in case it's not obvious to you, the real giveaway is the attire, okay? Experimentalists wear ties, and theorists wear suspenders. And that's how you tell the difference. Okay, I should give you a few examples of the different types of physics. So this is small-scale physics. This is a photograph of the experimental hall for the ATLAS collaboration at the European Center for Nuclear Research. And there for scale is a human being. And so small-scale physics doesn't mean small equipment, and it doesn't mean small collaborations. The author list on this experiment is pushing 2,500. You have to have a separate publication for the author list. So small-scale physics involves big money physics, big in many ways. It also, I think, fairly involves big questions. So it's a small field with big questions, and the kind of questions that you ask when you're doing small-scale physics are some of the things that we mentioned. Like, what are the smallest constituents of the universe? Are they quarks, leptons, photons, gravitons, and whatever else? Or are they maybe little loops of string? And what are the underlying interactions of those fundamental constituents? And I suppose I phrased the question here as with some prejudice. What is the underlying interaction of everything? So someday we'll get to a theory of everything that describes everything all at once. There are other similar questions which are, I think, very profound in this discipline. Where does mass come from? We actually had a partial answer to this come out in 2012 with the discovery of the Higgs boson, which is the element in the theory that actually governs the masses of different particles. So making progress on profound questions like this. Why is the universe made of matter? And the context for this question is, why is the universe made of matter as opposed to antimatter? Because the laws of physics, as we construct them, are almost symmetric between matter and antimatter. And so why would Mother Nature create more of one and not of the other? It's fairly safe for me to bet that when I come over and meet one of my colleagues that I haven't met before and shake his hand, we're both safe. And by touching each other, we're not going to be annihilated. We're both made of matter. And that's kind of an interesting puzzle that people struggle with. And then we have some practical questions like, can we make black holes in the lab? That would be cool. So that's small scale physics. Medium physics encompasses such an enormous array of research that I can't possibly do justice to it. I can't even begin to list it. However, I will recognize that often medium scale physics is kind of thought of as coming in two classes, kind of two styles. There's the technological, gee whiz, Big Bang, technically sophisticated approach to medium scale physics. And here's kind of one of my favorite examples. So this is a photograph of a dilution refrigerator, which is a pretty complicated piece of equipment that a lot of my colleagues have. And it's a device used to cool materials to within a fraction of a degree of absolute zero. Wow. It's actually a technology that's been around for a while. It's actually invented 70, 75 years ago, but it's been refined a lot in recent years. And there's some very interesting things you can study when you get down to very cold temperatures like that. And here's an example that I think is totally cool. If you take helium-4, which is a common isotope of helium, and you cool it down to about 4 degrees above absolute zero, it becomes liquid. And if you cool it down further to about 2 degrees above absolute zero, it does something very interesting. It turns into a superfluid. A superfluid is a fluid that flows without any viscosity at all. It is a perfect fluid. And the reason it does this is a kind of a subtle consequence of quantum mechanics that I'm not going to get into, but basically, very cold, very, very cold liquid helium flows without viscosity. It flows without friction. And this was a puzzle for some of the first researchers to produce superfluid helium, because several other things happen with liquids. You put liquid in a container, and you know there are adhesive forces between the liquid and the container wall. So if you take water and you put it in a graduated cylinder, you know the level of the water, if you look at it carefully, it's not perfectly flat. It produces a meniscus and rises up the side of the wall. And it won't go very far up because there are also forces between the molecules of the liquid that kind of hold everything in place, so it only creeps up the wall a little bit. In a superfluid, there's no impediment to creeping up the wall. There's no viscosity. So we'll actually make a really thin layer and creep very high up the walls of the container. A very thin layer all the way up to the top of the container, so not too tall, and over the top of the container, and then it will siphon itself right out of the container. The first researchers who did this, had their little, tiny, minuscule test tube of liquid helium in it, and then just emptied itself out. Is it cracked? It's a glass tube. And we did it again, and it happened again. It took them a while to figure out what was going on. So this is the kind of, technologically sophisticated, medium-scale physics that's done, which I think is totally fascinating. On the flip side, there are some medium-scale physics which is not technically sophisticated at all. I mean, some physicists study, granular flow of sand in an hourglass, or cream mixing in a coffee cup, or the way in which paper crumples and folds. I mention this because actually some of my colleagues at Amherst have recently been delving into the laws that govern the folding and crumpling of thin sheets, which is a surprisingly rich field of physics in order to try and correctly describe how a thin sheet crumples and folds. And I heard this wonderful talk a couple of years ago about the physics of baseball, which is actually rich in physics. Why does a knuckleball go so crazy? When you throw a curveball in baseball, it's actually the spinning nature of the baseball that actually causes the curve. It follows something called a malus force. So the the side of the baseball heading into the wind behaves a little bit differently from the side of the baseball spinning away from the wind, and the forces on the two sides of the baseball are not the same, so the ball consistently curves in one direction. Well, in a knuckleball, the ball is not spinning, at least not very much, not very fast, and the spin doesn't have the effect. It's actually what controls the airflow around the baseball is the seams on the baseball. And if they're oriented this way instead of that way, the baseball moves differently. So as the baseball is moving towards the batter and it changes orientation even a tiny little bit, it will change direction as it goes. And a knuckleball is actually a very chaotic pitch. In all of these cases, even in medium physics, kind of the theme is similar. We're trying to find the simplest, most basic underlying rules that describe the behavior of the thing we're looking at. And you can tell that by one of the hottest buzz terms in the business. It's called emergent phenomena. When physicists talk about emergent phenomena, they're talking about trying to describe the behavior of fundamental constituents that are described by a very simple set of rules, and recognizing that when you put a lot of these things together, these simple components can actually produce very complex and rich behavior in a macroscopic collection of those things. And so emergent phenomena is kind of a buzz term in this field, and it describes a lot of what's done in medium scale physics. I liken this to kind of the nature of computer programming, right? I mean, you can write a very, very complicated computer program in a high-level computer language, but ultimately, every computer program can be boiled down into a sequence of 4 logic gates. If you know how to do logical and, logical or, logical not, and logical exclusive or, all computer languages can be reduced to 4 elements. And that's kind of what physicists are trying to do in many cases. They're trying to find the underlying constituents that can be described with simplicity that lead to this very complex and rich behavior that we see in the macroscopic system. Most of biophysics fits within the medium realm, independent of medium realm, independent of whether it's looking at microscopic DNA particles or animal-sized objects. This is an opportunity for me once again to notice the difference between, let's say, other sciences and physics. The difference between biology and biophysics. Well, a biological geneticist would probably look at a piece of DNA and appreciate the rich depth and variety of DNA and all of the stuff encoded in DNA, and maybe would try and answer a question like, well, okay, which of the bazillions of genes in DNA might encode mutations for cancer? A biophysicist looking at a piece of DNA would look at a piece of DNA and say, oh, hey, that looks like a spring. I wonder what happens if I stretch that apart and I go. I wonder how fast it snaps back. Let me measure the spring constant of that. And I'm not kidding. That's what biophysicists do.
They certainly do.
So that I think illustrates the way physicists think a little bit different from other scientists. And the same thing is reflected in the way we teach physics, I guess. In my introductory courses, when I sometimes look at physics applied to human beings, I tend to look at it rather differently from the way other disciplines look at human beings. Biologists appreciate the rich variety of the human anatomy, and psychologists all of the depth of human thinking. In my introductory physics courses, when we talk about human beings, mostly we're talking about human beings as projectiles. Like, throw one up in the air, how long does it take to come down? That's what human beings are for. And then finally, there's big physics, which is things, planet-sized and bigger. Whenever I'm talking about topics in big physics, it's kind of usually the slide I like to do. Does anybody recognize what this photograph is?
The Hubble Deep Field? The Hubble Deep Field?
It's the Hubble Deep Field. It was published, I'm going to say, 2004, so it was a very long exposure of, taken with the Hubble telescope, taken of a very, very empty piece of sky. The field of view here, this is across the entire field of view, is something like 5/100ths of a degree. If you look at this photograph, there are only three isolated stars in this photograph. that's one of them. There are not three, because there's a third off the screen there. And there's one somewhere in the middle that I've lost track of. Maybe that's it. That's one, that's another, and there's a third just off screen. Every other speck of light in this photograph is a galaxy. And it is just amazing. There are roughly 10,000 galaxies in this field of view. So that's big physics on the really grandest scale. And it involves things, galaxy size and larger. That's what big physics is really looking for. And it involves some very interesting questions. The typical questions that big physicists look for. How does gravity work? Gravity is actually a very weak force. We don't notice the effects of gravity in everyday life except when pulled by really big objects like the Earth. So you got to really look at a grand scale in order to see the effects of gravity. And if you look out in the cosmos, the dominant force acting between the planets and galaxies is gravity. So that's the place to study gravity. What's the nature of space and time? Einstein taught us that gravity is intimately connected to space and time. If you really want to understand the fundamental issues in space and time, big physics is the place to do that. In recent years, or in recent decades, actually, big-scale physicists have also uncovered a couple of surprises that they never anticipated. In recent decades, we've explored a little bit more of our own galaxy, and we recognized that, we don't know that much about even our own galaxy. We've at least recognized our ignorance. So we can actually measure the mass of the galaxy. The way you do that is you look at some star at the very outside edge of the galaxy, and you see how it's orbiting the outside perimeter of the galaxy, and you see how fast it's moving. And according to how fast it's moving, how it's moving, figure out what the force on it is, because we know mechanics. And once you know the force on it, then you know how much mass must be pulling on it to produce that force, and you calculate the mass of the galaxy that way. And the answer is, the mass of the galaxy is 5 times larger than what we can see. And we know about a lot of the stuff in the galaxy. We know about planets and stars and asteroids and gas and dust. And if we add up everything that we know about in the galaxy, it accounts for 20% of the necessary mass that's pulling on that outside star. So there is something else in the galaxy that we have never seen and never anticipated, and we don't know what it is. But we have a word for it. We have a name for it. And the name is?
Dark matter.
Dark matter. And we call it dark matter because it's dark. You can't see it. It apparently does not interact with light. It does not interact electromagnetically. It is invisible in the deepest sense of the word. It's dark matter. And we don't know what it is. We have some speculation, but nobody really knows yet. And we're trying to find out. Okay, that was not the biggest surprise. The biggest surprise came a little bit later. It came in 1998 with the publication of data looking at distant galaxies, distant supernovas and distant galaxies. And we discovered, on an even grander scale, there's something else out there that we really don't know what it is. Scientists looked at very distant supernovas, and they were measuring how fast those galaxies containing those supernovas were moving and where they were located. And they discovered that they're all moving away from us, which is, we've known for a long time. We expect that, actually, because we think 13.8 billion years ago, the universe started with the Big Bang, everything's flying apart ever since. But of course, gravity is the dominant force in the universe, so you would think even if it's flying apart initially, it ought to slow down, right? Because as things are moving apart, they're gravitationally attractive. So they ought to slow down, and maybe at some point they stop and turn around and come back together. Okay, but that's not what these scientists discovered in 1998. They discovered that things are moving apart, but they're accelerating as they're moving apart. They're not slowing down, they're speeding up. So something must be out there causing that. We really got no idea what that is. I mean, really got no idea. But we have a name for it. And the name is?
Dark energy.
Dark energy. And we call it dark energy because
We don't know
it's
what it is.
dark. And because matter was already taken, it's got to be something different. It's not dark energy. And we don't know what it is. This is kind of one of the forefronts of the big science of the story. All right, so that's small, medium, large physics. These days, many physicists who haven't previously thought about data management have to start thinking about data management. We don't do that in my field. Big collaborations, we've been thinking about data management for decades. So medium-scale physicists run by kind of single PIs, or just a couple of people. You know, in order to satisfy funding agencies, have to make their data available in ways that they haven't previously thought. And I know that some institutions, like in Cornell, for instance, have faculty training programs in the library teaching them how to best. Rather than help in research, it is my opinion that physicists mostly need help in teaching, or could use help in teaching. Physicists are not going to think to ask for this, so we would have to be proactive if you're going to actually be an aid along these lines. But there are many ways in which librarians provide services that I think are incredibly valuable here. Physicists know how to find textbooks even when it's kind of a challenge. If you're teaching an introductory physics course, you have a choice of 191 different textbooks, all of them over $150 a piece. And physicists know how to figure out, what's a reasonable textbook. The answer is they're all perfectly reasonable. In fact, they're all essentially the same. It's embarrassing to plagiarize from each other. But I know that, librarians and other institutions are often very helpful in providing motivation to move in the direction of open source resources. And certainly, me and a lot of my colleagues are happy to do that and delighted to kind of move into open source resources where our students are not spending outrageous fortunes for textbooks that are going to burn at the end of the semester. The one impediment that you may not think about for physicists is if you're a physicist and you're teaching a large introductory course to physics, you have to worry not only about a textbook, but you also have to worry about an online homework system, because guaranteed you do not have the several hundred TAs you need to grade 1,000 papers every week. You need an online grading system, and publishers have figured this out also. So, textbooks were once the big expense, but now that you can pretty well get by without a textbook or use an open source textbook, now online homework is expensive, and students can easily drop $100 for the privilege of having their homework graded every semester. So we haven't found a way around this, but definitely this is a forefront of research that we want to pursue. And I think this is going to be a point of friction between publishers and readers for times to come. And it is kind of like the battle between code makers and code breakers. So right now, publishers, have proprietary rights to a lot of online homework systems, either offered by the publisher themselves or offered by a third party that is contracted with the publishers. It's going to be interesting to see how that develops in the near future. And it's also interesting to see how the technology is going to develop in the near future, because these used to be fairly simple systems that provide, a problem, and then the student types in an answer, and you get feedback saying whether it's right or not. There's a lot of movement into adaptive learning in these systems, where a student does a problem and gets it right, and is given a new kind of problem, or gets it wrong and is given another problem of the same type, so that the system adapts the content according to the responses of the student. It's a very interesting process, which might actually be a much better way of teaching students and getting them to focus on their weaknesses and develop better. That's kind of what we see right now. There's a lot of ancillary materials that physicists pay attention to in this age of flipping classrooms. There are sources of physics lectures that are quite good. Those will be open here. You can find online. Physicists are also interested in demonstrations and lecture demonstrations in classes. This is often a big part of a physics classroom. And there's the Physics Instructional Resource Association, which has kind of organized that approach, in effect, developed a catalog system for cataloging physics demonstrations, and maintains a list of different universities that provide online information about their entire collection of physics demonstrations with some good videos of physics demonstration. Large course teachers are very interested in test generators. Here's kind of a summary of test generator softwares. There's a couple of organizations that physicists pay attention to when they're looking for teaching resources. There's the American Association of Physics Teachers, which has several lists of useful items. And more generally, there's the National Science Teachers Association, which is physics. There's a couple of journals that are very closely geared to physics teaching. There's the American Journal of Physics, which publishes material which is kind of the undergraduate physics level mostly. And there's especially the Physics Teacher, which focuses on physics teaching issues, both at the zero and so that's kind of an overview of the stuff that we use, that there may be some of the stuff